Can we detect a single graviton? How does gravity affect quantum decoherence? And what's the actual difference between testing quantum gravity and probing gravitational effects in quantum systems? My name is Davide De Biasio. I'm a member of the International Society for Quantum Gravity Outreach team, and I had the pleasure of discussing these questions with Dr. Igor Pikovski, who explores the intersection of foundational and experimental work in gravity and quantum mechanics. It's been a fascinating conversation full of surprises. Now it's time for you to sit back, relax, and wonder whether the tiniest traces of gravity might soon show up in our labs. People often say that we expect quantum gravity effects to become relevant at super high energies we might just be able to probe when we manage to build a particle accelerator as big as our galaxy. So starting from this take or this perspective, do you think we should just forget experiments in quantum gravity, accept the state of affairs and move on to something else? Or is there any hope to experimentally probe the quantum properties of spacetime?
Yeah, this is a great question. The short answer is there is a lot of hope for experiments for quantum gravity. But this answer is at odds a little bit to the traditional thinking, I think, that we had for many decades. And so what you say is right. For a long time, we considered kind of quantum gravity scales to be synonymous with extreme high energy scales, or maybe black holes. And so there were maybe Gedanken experiments, or there were maybe ideas what physical effects might appear there, but no hope for experiments per se. But things changed in recent years for two reasons. One is there's a different theoretical perspective, which is less focused maybe on this kind of ultimate problem of quantum gravity, which maybe really is kind of mostly relevant at these extreme scales. But rather, it's a quantum foundations and quantum information perspective, which asks simpler questions somewhat, but then maybe equally deep. Not so much about the full theory, how it might look like, but rather about complex interplay of some of the fundamental principles of these two theories. They don't really match. So that's one part of it, that there could be interesting experiments that really see this complex interplay, which arises much earlier, on much smaller scales, much more accessible scales, it turns out. And the other development is really experimental, that a lot of fundamental physics today is approached in a complementary way, not anymore necessarily only in a kind of a high energy setting where you just smash things and see what they're made out of, but rather also through intricate tabletop experiments which leverage quantum technologies. So really quantum technology development of quantum information science. And it turns out that approach is extremely fruitful, both because it opens new possibilities to test fundamental physics, but also because it is a huge technological development, exponential development in the last decades that one can piggyback on. And so with those two different perspectives, it turns out, and this is a very rapidly growing new field in the maybe past 10, 20 years, it turns out there's actually a lot of possibilities for quantum gravity tests that don't require reaching the Planck scale.
Well, first of all, thank you very much for the complete answer. And I'm sure this will get our audience excited. So I will try to
Get me excited.
one after the other, and me as well, I promise and assure you. Now, before getting to the most modern and contemporary kind of developments, the ones we'll get to towards the end of our conversation, can we do kind of a step back and start from your first works in this kind of in field, right, concerning experimental probes of the interaction between gravity and quantum mechanics, and perhaps start from those optics papers you worked on something like 15 years ago. So am I correct?
That's right, yes. Yeah, I'm happy to chat about it. And it's really just a coincidence. I kind of fell into this field just at the very beginning of its development in many ways. I can say historically, I was a student actually at Santa Barbara, an exchange student, and I was very excited to do fundamental physics. I think like many students, I was excited about the big questions, gravity, quantum gravity. I was very interested in these, very big open questions in physics and tried to contribute. But I was a student from Europe, and in Santa Barbara, I was trying to do research. So they sent me, they said, look, why don't you talk to this European professor we have here that is from Europe? And, he might know better what your requirements are for a research project. Because I wanted it to be accredited. So this is completely random. I went to this office as an experimental physicist. I was not interested in experiments. And then I see he had all these books on gravity behind him. I asked him, like, well, I want to do a project, but I'm interested in gravity. And then he said, well, you know what? We are trying to test quantum gravity in the lab. And that was Dirk Baumeister. And he had a paper with Roger Penrose at the time, which I was not aware of, that discussed the possibility that maybe gravity and quantum mechanics meet in an unusual way. Maybe somehow gravity is more fundamental than quantum mechanics. That is kind of Roger Penrose's maybe fundamental philosophy, and which means that quantum mechanics breaks down potentially at some scale. And you could test that. That is not a philosophical question, and it's not a Planck scale question either. And you can just test it in an experiment if you could do a sufficiently large quantum object. And it turns out I never heard of that. And it turns out this experimentalist, Dirk Baumeister, was working on that. So that blew my mind that you could do experiments to test something, at least something about quantum gravity. It was not something I ever imagined was possible. I was very excited, and I joined his group, and we did some very interesting work, kind of trying to understand better how do you build this experiment. It's very hard. It still hasn't been built. It's very hard, but it's a path. It's a possibility. And that really started me in this field very early. So that was 2008. And maybe the next question for me, the most exciting question was, is there something else out there? Look, we have some example that we don't have to go to the Planck scale to ask interesting question about how gravity and quantum mechanics meet. And so that has been my trajectory since, where I've been exploring how we could potentially test maybe some other aspects or maybe some other possibilities of quantum gravity, which would show themselves in real-world experiments. One example is, for example, one early paper I had in 2012 working with the group also of Markus Aspermeyer on optomechanics, which showed that you could use also these massive resonators that you also need to test Penrose's conjectures. You can use it to test some completely different model of quantum gravity. Namely, there is ideas in quantum gravity floating around that maybe the Heisenberg uncertainty principle has to be modified. And again, these models usually assume that's only relevant in the Planck scale. But if you work with them seriously, if you incorporate it in quantum theory, there are side effects. And so there's other effects that arise because you break quantum mechanics a little bit. And quantum mechanics is very robust. So if you start breaking something a little bit, there's some side effects that arise. And we show that actually this type of model, even though in principle they're only on the Planck scale, you can scale them up. You can scale it up in a clever scheme such that suddenly you have some nonlinear enhancement of these effects that you would see in a quantum optomechanical experiment. So it was really one of the first demonstrations that there is actually more type of tabletop experiments you could do that could at least, at the very least, do null measurements. They could test these models and say, look, that's not how it works, and that's already input. Or more excitingly, maybe they'll confirm. So there've been many experiments since then that test this model in this spirit and other ways as well. And so far they're null experiments, but they constrain some of these quantum gravity models with real world data. And I think that's for me the most exciting aspect about it. Just as we maybe test dark matter models, that we have many experiments that don't show anything, but we still learn something about it.
Well, it's interesting that you mentioned this interplay. People expect the maybe between quantum mechanics and gravity as intended through a general relativistic lens, right? Space-time being curved and Heisenberg uncertainties principle maybe being altered. Because one of the aspects which is often brought up of quantum mechanics when talking about its interplay with gravity and the ways it might be modified by implementing dynamical spacetime is decoherence. And you've worked on decoherence and in particular the interaction between decoherence and general relativistic time dilation. But before getting there, I have the feeling that even among physicists, there's many people that do not actually know what decoherence is. So may you please tell us something about decoherence as such, and then we'll move on to your work in particular.
Yes, of course. Decoherence is a very important fundamental concept of quantum theory, which really has only been properly understood maybe in the 80s with the work of John Wheeler, Zurek, Wouters, and others. And so it is a little bit of a subtle concept, but it's so important today, especially for quantum technologies. Like we all know, for example, that the main challenge of quantum technology, or we should know, is that overcoming decoherence. Now, what does it mean, decoherence? Maybe in simple words, is the following statement. Quantum mechanics is much more rich than classical physics. It allows so many more possibilities of existence at the quantum level. And we call them usually superpositions or entangled states or something like that. But it's really many, many more forms of possibilities of states or just of how nature could be that exist at the quantum level. So if you have a superposition of different properties, you really have, in some sense, a new property arising. But we don't see those in the macroscopic level. So it's a little bit like imagining maybe, we can see all these colors, but then there's a lot of maybe wavelengths we don't see. And it's a little bit similar for the quantum world, that there is actually something more than that. There could be superpositions of something like red and blue in simple analogy. But we don't see those anymore. And the question is, why don't we do that? And decoherence explains that to say that these special forms of existence are very fragile. They're so short-lived if they are interacting with other systems. If there's any small disturbance, it just will immediately destroy them. And that's the challenge for quantum computers, because they actually exploit these superpositions. They exploit this new form, this parallelism, where you can actually do something better with these additional states that you have to work with. But they're very fragile, extremely fragile. And so to isolate it is hard, and they're much more fragile than kind of classical energy. And so that is what we call decoherence. Decoherence is this loss of these kind of unique quantum properties in some sense, and it's extremely rapid. And so that's the core of it.
Yeah, I would say that there's an interesting duality, right? You mentioned, because decoherence is one of those things that are well understood and done part of the work of people working in quantum technologies. And on the other side of the spectrum, of people working on the foundations of quantum mechanics as such, and perhaps don't really enter the work in between the two extrema, right? One of the things, on the other hand, that people tend to understand about theoretical physics, or at least have heard about when discussing quantum theoretical physics, even at an outreach level, is time dilation within general relativity. And I know you've worked more or less on some ideas to test the effect time dilation might have on decoherence in quantum systems. So I would like to hear something about that, if you don't mind.
Yes, I'm very happy to chat about that. That's what you're saying is exactly right. Decoherence can arise due to many, many different reasons. So there's all these different interactions and just noises that all cause decoherence. Now, what I mentioned before, my main interest is usually how does gravity affect our quantum systems? What does it do? And one of the early questions we were wondering was, is there something that is really truly unique to gravity that we can isolate in the quantum realm? And what do we mean by unique to gravity? Well, at the level of just forces, there's nothing special about gravity. We have the Newtonian force. Well, we also have the Coulomb force for electric forces, or many others. And on this level, we can actually see and observe in experiments the effect of gravity. Now, there's very simple ones. We can drop atoms or something. So, okay, they fall, so they feel the gravitational force. But you can go beyond, and these are very beautiful experiments and actually insights from the 70s still, where you could see a unique influence of gravity in the quantum realm. Namely, you could see something, how superpositions, these quantum superpositions, which only exist in the quantum realm, are affected by gravity. And these are experiments in the 70s have been done, and then later first with neutron matter waves. So this is basically double slit experiments, interferometers that feel the gravitational force, and they can see how this force affects superpositions, and you can measure it, and it affects superpositions in exactly the same way as any other force. But it's an interesting insight, because you can see that, oh, look, we can add gravity essentially to the Schrödinger equation. We can work with the Schrödinger equation because we're describing superpositions. And we can add the gravitational force just as we're adding any other force, and it works. it gives the correct predictions, and we can measure it. But what we were interested in is, could we go beyond that, namely something unique to gravity, which doesn't look like a force anymore? Because Einstein's insight is precisely that this force picture is really just a limit, it's a mirage. It's not actually true. Whereas, as opposed to the picture for all other forces, says, yeah, it is actually a force. We just maybe have a quantum picture for it, but it's a force. But gravity says, no, it just looks that way. And actually, it's curvature of space and time. And so one unique feature that I've been always fascinated about is that gravity changes time. It bends time. And that is really something that only gravity does, as far as we know. And so we measure that often. And this is this famous example of the gravitational redshift. And basically what it predicts is essentially that your feet are younger than your head. And so there is time dilation, meaning that time is actually much slower if you're closer to the ground than the time flow further away. And for us, I don't remember, I think it's something like a few nanoseconds over a lifetime, the difference. So it doesn't really matter so much. But if you have precise clocks, we can really measure that. And people do that routinely. So we can measure these on millimeter scales, that time flow is really different. And so what we were interested in is to understand if we include this phenomenon truly kind of on the quantum level, we should have something, we should maybe have some new effects. And the basic idea was, what if we take clocks that are themselves quantum mechanical, in a sense that they don't even know where they are. They're in superposition of different heights. And then what you would get is that you should also have the gravitational effect, namely that these clocks are simultaneously younger and older than themselves. So they tick simultaneously at different rates, but it's only one clock, it's just in superposition. And then you have to now kick in the Einstein gravitational effect of also that their ticking rate is also different. And so this was a way for us to combine some fundamental principles of quantum theory, which is the superposition principle, and of general relativity, not Newtonian gravity, but really of general relativity, namely that the time flow is different. And so what we studied, this is also work from about 10, 15 years ago. What we studied is there something interesting at this interplay? Namely, if you have systems that can record time, but they try to be in superposition, is there something interesting that gravity does now to this? Because gravity changes the flow of time. And there it turns out, it was a bit of a surprise. And it turns out, yes, there's several interesting surprises that arise, new effects. One is that, look, you can actually see this interplay. There will be entanglement generated, and there will be a special signature, a unique signature in possible experiments, which are hard to realize, but people maybe now soon are getting there with the precision that they could see this interplay of general relativistic time dilation and quantum superposition. But there was a second, a little bit surprising outcome of this. Namely, it turned out that if your system that you try to create in superposition is big enough, it turned out that because of this interplay with time dilation, they will actually decohere. And that's something that I didn't expect, but that's just something that comes out from normal gravity. Namely, if you try to make an object which is consisting of many atoms, say a complex molecule, or a bigger object, what is actually happening if you zoom in, unless you're exactly at zero temperature, what actually is happening is there's Brownian motion. Like all these atoms, they wiggle a little bit, they move around. And usually it doesn't really matter. We can still move the molecule. We can do experiments with the molecule, even though all the atoms in its own atoms are all wiggling a little. But this effect of time dilation shows that it does actually matter. Because what happens is that this Brownian motion, this kind of thermal motion, is actually slowed down in the presence of the gravitational field. And then our prediction is that it turns out that just from normal gravity, just completely normal, you don't need quantum gravity or some kind of new physics or new theory. Just from normal physics as we expected, it turns out that precisely the slowdown of these thermal vibrations would cause the system to be decohere if we were trying to create a superposition. So it's one way it's one of many ways, but it's one of the mechanisms that kick in for a completely isolated system. If it tries to be in a superposition, like a Schrödinger cat state, it would actually immediately decohere just from the effect of time dilation. So that was one of the things we found, which kind of shows why it's impossible or extremely hard to have superpositions of large objects in the presence, at least, of time dilation.
Because it's really hard to screen gravity, or I would say impossible, right?
Exactly, it's even impossible. Exactly right. So you could be isolated. So that's the challenge of decoherence. You try to isolate these sources. But how do you isolate something like time dilation? And if you are, well, you could maybe go to space far away from gravity, and then okay. But even then, slightly different velocities will give you time dilation. But it's exactly right. You can't screen gravity, and so this is a phenomenon which is poses some practical limitations at least. But philosophically, it also shows that it's kind of natural that there are no superpositions that arise for large enough objects.
Well, if you're in space, you can always screen your lab from cosmic particles, but you cannot screen your lab from gravitational waves passing by, right? Which alter
Right.
dilation and all that. So I see,
Exactly.
I
Yeah.
see how deep this thing goes. If I can roll back for a second, because you mentioned a thing just passing by, which might be slightly confusing for people that may have seen quantum mechanics in a standard course presentation. You mentioned clocks. While in quantum mechanics, time is typically just some sort of external parameter with no weird quantum property at all. So, what do you exactly mean when you bring up quantum clocks, which will be obviously super important in trying to understand the quantum behavior of spacetime?
This is an excellent question and a very, very deep question. So there is, again, simple and more complicated answers to this. Now, in quantum theory, of course, time is critical. That's the whole point. In physics, our main goal in physics is to predict dynamics. We know something, how is it going to be in the future? And the Schrödinger equation does that for us in the quantum realm, for example. And what it tells us is, how will a system be at a later time? So time is very important, but just somehow as simply as a background tool per se. Now we can build timekeeping devices out of quantum systems. In fact, these are the best timekeeping devices we have. And for example, atomic clocks do exactly this. And what they basically do is they piggyback on the fact that atoms have discrete transitions. So one of the predictions of quantum mechanics is that there is some kind of discretization of energy. That's one of the big predictions, the first one, in fact, the birth of quantum mechanics. And that means that there is only very specific energy levels which are allowed in an atom, and they have a very specific frequency, a very specific transition between them. And so atomic clocks really piggyback on this pure quantum property in order to make a very, very precise measurement of frequencies. And a measurement of frequencies, it's equally means that, how well do you measure time? So nearly all timekeeping devices we have today that are good are based on actually quantum principles. But they're simply based on this kind of discretization of levels, and just that it kind of gives you a very precise tool. Now, what you're referring to is there is another deeper notion of time, which is precisely this curved space-time that comes from Einstein's theory. And quantum mechanics typically does not deal with that. But what we showed is that it is, and many others as well, but what we did is we focused on the fact that you can also incorporate this curvature of space and time in the Schrödinger equation. Basically, you get corrections. You get some kind of corrections to Schrödinger equation because you're actually not evolving with the normal time, but actually your time itself has to be a different time. It's a proper time. It depends on velocities, and it depends also on your mass distribution around. And it turns out that you can incorporate it in the Schrödinger equation, at least if it's small, if the effect is small. And what you then get is studying essentially quantum theory on curved spacetime.
Mm-hmm.
So many people studied that for decades in the other limit, what you mentioned in the beginning, namely the high energy limit. And that is known as quantum field theory in curved spacetime. So people studied how do kind of quantum fields behave when we are near a black hole. And then, and then there's particle productions, Hawking radiation. There's fantastic phenomena. And there's been a lot of research in this, and it's very, very interesting. And what we did is something a little bit complementary, just on a level kind of not on the high energy level, but on the low energy level. Namely, we started with a Schrödinger equation, and we looked at how will gravity beyond Newtonian gravity change our Schrödinger equation. And it turns out one can do it exactly, and it changes it with like small perturbations, and we can incorporate it. And what it really captures, one of the effects it captures is precisely that the time is no longer a fixed, simple parameter, but it's actually a more complicated object. And so we can incorporate it mathematically, and that gives us these predictions. And one of the predictions is precisely, if you do that, then you see that there will be decoherence of composite objects. And you wouldn't have it in the normal evolution, as an example.
Well, thank you very much. And thank you for bringing up quantum field theory in curved spacetime, because quantum field theory in curved spacetime is often referred to as some sort of intermediate step between QFT without gravity and proper quantum gravity as such. And this more broadly connects to the fact that many of the things we mentioned today kind of involve quantum plus gravity, understood in a general relativistic or even Newtonian sense for weak fields. But do you think we can still understand something about quantum gravity as such passing through quantum plus gravity, or there's no hope to do that?
This is an excellent question. I think yes, you can learn a little bit about it. I think one has to be careful that, let's say, in this particular type of a field or model, we really are trying to treat gravity just classical in this framework. So if you say quantum field theory on curved spacetime, or in my case, it's really just quantum mechanics on curved spacetime. So not fields, but just an atom. Let's say an atom feels curved spacetime. There's new effects that arise from curved spacetime. Why I like the atoms is because now you're close to experiments. You can actually design experiments that could test that and see that. So you don't need to jump into a black hole or see some field theory effects. However, we try in this framework, we try to deal with gravity really purely classical. On the other hand, there could still be surprises there. So this is a field that we have, for example, zero experimental evidence so far, which is to say that maybe you're not allowed to include curved spacetime into quantum mechanics. Maybe it's just forbidden. I don't know what the new theory is, but maybe it just doesn't do that. You can put a Newtonian force in it, but not beyond. And this would be completely consistent with every single experiment or every single observation we have so far. And so even though it's not consistent with our mathematical framework, that's not what we expect, we don't have any empirical evidence for that actually being really true. And so there are surprises that could arise. So I would say this is not necessarily a probe of maybe quantum gravity per se, but rather really a limit of where quantum theory and gravity meet in an entirely new regime where there's zero experimental evidence. And historically, that's the only way we made progress in physics. We really just explored new areas, and nearly always there are surprises that arise. So I think this framework, let's say, for example, our prediction is like, if you put molecules, complex system in curved time, they will decohere. And this prediction assumes that we can extrapolate the mathematical formulas we have into this regime. But it may or may not be true experimentally. And that would really tell us a lot about maybe something doesn't work. But at the core, you don't need to quantize gravity to ask these questions here.
Yeah, I fully agree with your take. And precisely as when you walk on a mountain, every step kind of constrains the next one. So I totally see why this can be important for quantum gravity as such. Now, we are on the YouTube channel of the International Society for Quantum Gravity, though. So I need to ask you a question which kind of goes towards quantum gravity, how it is usually intended. And one of the features most people expect from a theory of quantum gravity, at least in some limit, at least in some regime, at least in some approximation, is the presence of some sort of graviton, a particle mediating gravity. So, and this is a loaded question, of course, but is there any hope to experimentally observe a graviton or any interesting development you've worked on recently?
Yes, Yes, the short answer is yes. It turns out that also in this limit, when you quantize gravity, you can actually design experiments that can really observe gravitons as they are predicted. And if you had asked me maybe 2, 3 years ago, I would have said no. But we had a recent result from our research group where we showed exactly that you can actually detect single gravitons exactly as they're predicted by normal linearized quantum gravity. Now, this sounds somewhat against conventional wisdom, and it's true. The conventional wisdom has told us for many decades that it should not be possible. But it was simply overlooked. It's not actually particularly difficult compared to the Planck scale or other things. And there's reasonable experiments that can be performed. And it's simply something that has not been thought about in the right way, namely how to actually do that such that it works. We knew many examples where it doesn't work. And then this conventional wisdom arose that, look, you just can't do it. But it just turns out that these examples of how to detect it were just not good examples. And there's a much better way of doing it, and it absolutely works. So we had this recent result that shows you can detect single gravitons, and there's no tricks, there's no semantical ambiguities. It really is just exactly as we expected. You could do it in very similar way as people detected the single quanta of light 100 years ago, the famous photoelectric effect. Basically the very similar spirit, just adapted amid to quantum gravity challenges.
Because this is absolutely exciting. And if I'm correct, what you refer to as common wisdom or shared wisdom or common knowledge or something like that is the idea that, okay, gravity is weak, so we expect quantum gravity effects to appear in the high energy regime, as we said a few times today. So in order to measure a single graviton, we would need a super strong source and a super sensitive detector, right? Something of the size of a planet or something like that. You've heard those things in conferences and in outreach in particular. So why does your approach, your experimental or imagined experimental setup kind of deviate from this common wisdom? Where do things go in another way?
This is really an excellent question, and I have asked myself the same question for a long time. That's why I have a very clear, I think, and short answer, because I now really understand where it deviates and why it works, which is why I'm confident that everything is fine. Because I was asking myself the exact same question when thinking about this. It was an idea I had many years ago, even as a postdoc, where I realized that, look, it should actually be possible to see single quanta of gravity from gravitational waves. And the basic idea is very, very simple. It's something like this: that, look, you start with a system which has discretized levels. Okay, typically it's an atom, but gravity couples to mass. And so let's not take an atom. Let's take a system that I used to work in quite a lot, which is, again, optomechanics. So you have a very big, large system. It has a lot of mass. Well, if you can isolate it well, and if we can. I worked with a group, for example, that worked on superfluid helium detectors, just for gravitational waves. A group of Keith Schwab and Caltech. They can build a superfluid container, and it just sits there. If you excite it, it just sits there, and it will never decay. I mean, never is a bit exaggerated, but we capture it by what's the dissipation rate of the system, no matter due to whatever, and it's just extremely small. It just sits there for a long time. So my thought back then was like, well, why don't we just prepare that in say a quadrupole transition, or just an excited state which has a quadrupole transition, and we just wait. At some point, it should emit a graviton. At the very least, it should do that. And then when you run the calculation, it turns out that actually, because it has a high mass, that actually, especially in the presence, if you have high sources, it can have a stimulated process. It would be extremely large. So yeah, it would emit a graviton in 1 second. But then I sat on it for many years, because I thought, look, this goes against conventional wisdom, and there's much better, a lot of smart physicists show that it can't be done. And so, it was hard to square. I thought it must be wrong. But the short answer is it's not wrong. And it's just a different process than what other people have considered. And namely, in one sentence, the answer is the following. We had calculations by Steven Weinberg, by Freeman Dyson, by many other, by Rothman and Born, many, many excellent physicists, and they asked the exact same question. But the difference is they thought about atoms. And not just atoms, they thought about electrons. So the typical quantum system they were thinking of is, let's say you have an atom and it has electronic transitions, because that is your typical classic quantum system. And then you compute how long does it take to detect a graviton. And it's exactly what you say. Well, let's make a whole planet out of these atoms. Let's look at all the possible probabilities. Let's have a huge source, and even then it will take 10 years to detect them. But the point is that this is a little bit like trying to build a radio antenna out of plastic. It just is a very bad detector. It's a very bad process. And what's beautiful about gravity, it's universal. It doesn't just couple to electronic transitions. It couples to all other possible transitions. What we looked at is something else. We looked at acoustic transitions. And the difference is it's not that the graviton will try to kind of push an electron down with respect to an atom, but rather it's trying an entire bulk to squeeze a whole huge system consisting of many, many atoms and trying to convert it into a phonon, into an acoustic transition. And this process is by far stronger. Now, the reason people haven't thought about it in the context of quantum mechanics is because we think about these systems usually classically. Look, this is now a big macroscopic system. However, these new developments in optomechanics and acoustic mechanics show us that we can actually access really single quanta. We can prepare it in quantum states, and we can measure quantum states also on macroscopic scales. And that was unthinkable long ago. So essentially, the trick is really you build a different type of detector, which piggybacks on the fact that you have a large mass quadrupole, essentially. That's what really couples. And that's exactly what classical gravitational wave detectors do. They don't make atoms, they make large detectors. We know it scales with mass and length. However, now we can also think about looking at quantum transitions inside. And that's all we need to do. So the only aspect of the atom that's important is that there's discrete transitions. Namely, it exchanges energy in discrete steps. And that's what we mean by a graviton. That really is all there is to a graviton, at least at that level. So it has, of course, many, many other properties, which would be interesting to test. But at a very fundamental level, what a graviton simply means is that my gravitational wave consists of discrete chunks of energy. And if we could see one discrete chunk, that is a detection of a graviton. And exactly that we can do with like a larger detector, which essentially just absorbs energy from the gravitational wave. Another interesting aspect of that, just to go back to what you initially said, one of the conventional wisdoms is exactly that gravity couples very weakly. Mm-hmm. And what's interesting here is that actually that is precisely what we exploit. Namely, what basically happens is that you have a passing wave, and let's say it consists of many, many gravitons, 10 to the 30 or something, many, humongous amount. And the probability of each individual one to be absorbed is essentially zero because it barely couples. But it's not exactly zero. And what you do is you exactly build a detector which maximizes the probability of just only one of them being absorbed. And the reason you actually get only one and not like millions and hundreds, it's actually precisely because it couples so weakly. So you actually want the probability to be low in the presence of this huge, humongous gravitational wave passing by. And so nothing happens, except at most, there's only one thing that can happen. There's like a tiny, there's a tiny probability you will absorb any one of them. But then there is a big probability that at least one you have absorbed. And so it's really kind of putting probabilities more in the focus rather than something else. It's just to say, look, it's very hard to do that. But if I have many, I can optimize the probability of just a single absorption. And that's all we need.
And more practically, do you think this sort of experiment is something we may be able to set up in the near future? I'm not asking whether there's any specific project in place, but whether there's hope of doing that.
Yes, absolutely. There is absolutely hope, and that was also a little bit of a surprise from our result. Now, in order to really maximize the probability of absorbing only one quanta of energy, which is, that means it's a click. It's like a photodetector. It means like you shine laser on it and it just does click. It means, okay, that was your one quanta of light. And in our case, you have your, maybe say, resonator, and it just, clicks essentially when there's one phonon inside. So that probability you want to maximize. That depends on what is actually your source of gravity. It depends on the frequency, how long does it last. Some of it just goes through very quickly because what LIGO detects, these black hole mergers, for example, what LIGO detects, they really last only a few milliseconds. And so for many of these sources, it will be really, really hard to really just absorb a single click, just because it's not good enough. Then you don't need a planet, but you would need like many tons, say, something that they were planning to build, Joe Weber and others, they were planning to build these detectors, many, many tons, in order to catch these gravitational waves. And that's hard. But it turns out there's one type of source for which it's really realistic that LIGO only detected recently. And that is a neutron star merger. So it turns out for neutron star merger, the type of wave that arrives is a little bit different. It lasts longer, and it has the right properties for which we just look, for example, at the data which we already know, which we already know from LIGO detection. It turns out for the very first neutron star merger that's been detected, for this type of source, you would have needed only a 10 kilogram detector. A 10 kilogram detector with the challenge of being at low temperature, so you have to cool it to a millikelvin, have a low dissipation rate, Q factor. So it's like a few orders of magnitude, maybe 2-3 orders of magnitude beyond state of the art of the 90s, because they haven't developed those since then. But still, 2-3 orders of magnitude beyond state of the art is not so bad. For that detector, a 10 kilogram system would have been enough. And so it really is very realistic to do that. The biggest challenge is really, it's not actually the isolation. It's really, for the following reason, there's also always this argument that, look, instead of a graviton, you could have so many other effects. How do you know? How do you know it wasn't like something else or something shaking it? And first of all, well, we can prepare these detectors to be very low dissipation rate. That's what I said. They do that already with superfluid and others. We know the dissipation rate is so low that, let's say on average, in 1 hour, nothing should happen. But now the question is, why is 1 hour enough? Or maybe 1 minute, let's say, to be on the exact, let's say we know in 1 minute, nothing should happen. No other source would interact. Why is it enough? Well, because we can piggyback again on LIGO. We know when they detect the gravitational waves. We would just, post data processing, basically find the time window when the gravitational wave passed. And it was just a few seconds. So our point is just, you only need to cross-correlate precisely. You only look at excitations only in the window when we know gravitational wave passed. And not just that, it has to have the right frequency and the right amplitude. So one can really basically cross-correlate and then know exactly this was gravity. But the main challenge, so all these other noise sources, I'm not too worried about. It's a technical challenge. The real challenge is quantum technology development, excitingly. Namely, what we need is a sensor which is sensitive to these small single transitions of energy. So it needs to really distinguish between 0 gravitons and 1 graviton. And this, we can do this discrete measurement of energy, obviously in an atom. That's what we do routinely. This is the atomic spectra. But we can also do it in very big systems. Recently, for example, at Yale, people have done it in Jack Harris's group, or in ATH, Evenchu's group. Sorry, not Evenchu's group. So there's developments in this direction where people really count quanta of energy in acoustic vibrations, but at smaller masses. So I think the current record is something like milligram or a little bit below. And we need to scale it up now, maybe to gram or kilogram. Maybe gram is okay, with some clever tricks. But that's where we need to scale up. So it's kind of the ability to do quantum sensing on a little bit higher scales than where we have today. So it's a challenge, but LIGO took 50 years to build, from the initial ideas to building. And in this case, I would guess it would take much less than 50 years. So it's absolutely realistic to do that. And I think if there's efforts and there's interest now, and people, it's anyway technology development is being developed. And there's maybe other ideas of similar form. Now that we know that it can be done, there's maybe better ways to do it. So you could bridge a few orders of magnitude just by thinking. So I'm extremely optimistic about the fact that there will be single graviton detection within, I would say, maybe let's say 2 decades. It's maybe my guess, which sounds long, but LIGO took 5 decades, so I don't think it's too bad.
I'm sure that at least to our audience, it will not sound long. Usually, when discussing potential experimental tests of quantum gravity phenomena, including gravitons, people speak of 20, 15 orders of magnitudes from where we are now. So this is absolutely on another
Absolutely right.
level,
And this
a
thing,
different
yeah,
thing.
right. And this theme is really because somehow you have to find the right modality to detect. And so just to reiterate, we're doing exactly the same as previous work have explored it. Just previous work was, well, the answer is negative, but the process with which they absorb gravitons was not optimal. You can do better because gravity couples to mass and length of a system, so you can do better.
Well, that's absolutely thrilling, and I can't wait to hear more about the future developments of this line of research. And in that sense, may I ask you what your, because you've published this, like this appeared and people have been discussing. So, what are the next steps for your research in particular?
This is a very good question, and again, it was a little bit random. It was not like, oh, you know what, I want to find out how to detect gravitons, and let's do it. So it's not like a planned research agenda, and so it's developing now a little bit naturally. One of the very first questions afterwards that I was wondering, in fact, with I hired some high school interns. They reached out around the same time. They were high school students that were interested in doing an internship. And one of the first questions we explored in this context was, how does this compare to the historic development of quantum theory? And it's a very important question because we are a little bit biased, especially in the modern technology, quantum technology kind of view. We are biased by what we already know. And so if we apply somehow our modern views of how do we test the quantum mechanics of something, we think about the modern test, like how do we test Bell inequalities? How do we test some unique quantum features? Some, I know we call negative Wigner functions or so, how do we kind of do really these complicated things that we do today, which we take as a benchmark? But for me, it was interesting to ask what was the benchmark 100 years ago? Because they were exactly right. They were all right and correct about quantum theory, and they didn't need these kind of modern tests. Now, maybe there were loopholes. So that's what we need. That's why we test Bell inequalities and other things. So maybe it's not, bulletproof, their type of test, but they were good enough to convince the entire physics community that we have to go away from classical physics into quantum physics. And that was even long before the development of quantum electrodynamics. So I wanted to understand that better, their reasoning. And so it was fun to work with these high school students because they're unbiased. And so we were reading old papers by Einstein, and we were reading about all the ways people were trying to shoot it down. Like, oh, that must be wrong. What alternative models did they predict? Because Einstein really predicted immediately in 1905, he said, look, if we see this discrete exchange of energy, it must be that there must be a photon. Really, you cannot go around it. The fact that the electromagnetic field, is no longer Maxwell. It's no longer a wave. It must have discrete energy. And nobody wanted to believe it. If even Einstein himself, he liked Maxwell's equation, and he just thought you can't go around it. He thought for 20 years, how could you go around it? And any way you try, it's a problem. Either you don't conserve energy then, or you have like contradictions with other experiments. Or you have other issues. And we were looking at this, what are these early experiments? And so that is one of my main goals. There was some inspiration for that to show that, look, we can actually really test and to some degree demonstrate that we can rule out alternatives to linearized quantum gravity. And I think that's the main thing. Because a lot of the maybe initial reactions to this paper were, oh, look, but it's just, you just absorb discrete energy, but are you really sure that you really need a graviton? Couldn't you do it in other ways? And yes, you could have some test models that also do it and they don't have a graviton. But these test models, that's the main insight. These test models are not normal gravity. They're not normal, even classical waves. It's some very funky interaction between like a wave you want to keep classical, but then somehow it has to interact with your quantum system. And these models, they don't conserve energy. They're not good models. Plus, there's other models, and that's my main interest right now, namely to ask questions, could we test very interesting property about quantum gravity that would show in such experiments? For example, could we test if it's a spin 2 particle? Could we test, for example, like the exact correct properties that, for example, very simple question that we came up with a high school student was, is actually Planck's constant the correct constant for gravity? Namely, if you have gravitons, according to Einstein's formula, it should have energy that's proportional to frequency and Planck's constant. But what if it's different for gravitons? And you would see that. So these are the type of tests that I'm excited about in the research direction. I'm mostly excited about to show what aspects of linear quantum gravity can we actually probe, and what alternatives could we rule out with such experiments.
So thank you very much. And thank you also for anticipating somehow my follow-up question, which would have precisely been whether these kind of experiments could also probe the features of gravitons. And in that sense, pressing a bit on this point, in order to single out stuff like, the spin or whether they actually move at the speed of light and stuff, people ask about gravitational waves, and you mentioned Planck's constant and so on. Do you imagine you would need to enhance the kind of detectors you mentioned before and described before, or is this something we could do straight away with the sort of setup you've already discussed with us?
I think both. I think some questions you can test with this type of setup. Like, again, a very simple test model, let's say, I could test whether the energy exchange in single quanta between the gravitational waves and the detector is really according to kind of normal Einstein's formula. E equals hf. And how do I do that? Well, I see that, oh, look, I'm getting some transition which has a certain frequency. And then LIGO tells me what's the frequency of my wave in this window. Like, what's the frequency? And then basically I can see, oh, does it match? Or maybe I always get double frequency. Maybe Planck's constant is somehow twice as big or twice as small in the gravity sector, just as an example. That you could immediately right away test with such a detector. You see individual clicks. So it's a very complementary detector to classical detections. In some sense, it is just a gravitational wave detector. The only difference is you really extract only single quanta. Because the normal gravitational detector, it has an average. It measures position. It measures some average. And here you just post electron just on single quanta. And then you see if basically this is consistent with each other according to normal physics. So this is the type of test we could do immediately. But I think then it's a very interesting question you ask, namely, can we go beyond and can we maybe combine these type of observations maybe with other tests that other people propose and other type of interesting phenomena. And so, for example, Frank Wilczek proposed an interesting question, namely, could we see maybe quantum noise of gravitational wave? And it's a slightly different aspect of kind of quantum mechanics. That's the beauty. The kind of quantum mechanics has many, many phenomena built in. And it's somehow, my dream is to have a multi-messenger approach to quantum gravity. Namely, that you kind of start testing maybe slightly different aspects, and then they themselves teach you something, but together they teach you much more.
Because each one of them kind of constrains your space of possibilities.
Right, exactly. And the consistency between them constrains us even more a little bit. So that's why I see it, because there's now several proposals how we could maybe test quantum gravity. Another very popular now is kind of to create big superpositions of masses and entangle them. And that's another set of proposals which is not related to the single gravity detection. It's a different one. And there the challenge is to create superpositions. For our proposal, we don't need any superpositions. You just need sensing. It's a different challenge. But if in the future you have all these different types of experiments, I think altogether they will be able to tell us huge amounts of information about quantum gravity.
So this is definitely thrilling, and I can imagine part of our audience, mainly that comprised of young students, perhaps even high school students who are interested in quantum gravity and experiments and phenomenology and a variety of different things we mentioned today, may be interested, and this is the way we may go towards the end of our conversation, in understanding how to enter such a boundary research line in which you have to know about general relativity and quantum foundations and sensing and experiments and neutron star mergers and gravitational waves and so on. There seems to be, and even statistical analysis, right? There seems to be so much to know to approach this kind of field. So, what's your suggestion to students that may have got excited about the work you discussed today with us?
I'm actually very optimistic about this and precisely this question. I would argue it's the opposite. It's so much easier to enter this field today than it was maybe 10 years ago. Why? Because before, the focus of quantum gravity was very theoretical, and it became complicated because it's the biggest challenge we have in theory, in over a century, and we have the most brilliant minds that have already worked on it. Einstein, Hawking, Carlo Rovelli, many people, many people you talk to. These are some of the most brilliant scientists you worked on, and so naturally, either you have to be smarter than them to make progress, or at the very least, you have to learn all these complicated tools like string theory. But this approach, let's say on this kind of question of where do experiments actually might see something, is in some sense much simpler, simply because quantum technology development really opens up novel opportunities. So it's much, much simpler, and we ask also simpler questions. It really, on the quantum level, basically my take is, look, maybe we're trying to just repeat some of this very early quantum tests and questions that people had 100 years ago. And so we might not even need this complicated framework of quantum field theory or other complicated frameworks we have today. And it's actually maybe helpful not to know too much, a little bit, kind of not to be biased. And at the same time, you're right, absolutely, that this is in between many fields. Exactly like you say, look, there's gravitational wave detection, there's quantum information science, quantum sensing, there is just GR. There's kind of this intersection of different fields, but it's not that you need to be kind of a deep expert in all the problems that the people study in these fields alone. Rather, there's new problems and new questions that arise at the intersection of this Venn diagram, which are in many ways often simpler to tackle, because you don't need necessarily this whole machinery of the field. Let's say you do gravitational wave detection. You really need to now, piggyback on also 50 years of research. You need to make very complicated predictions for mergers and so forth. And same for quantum gravity and so forth. But here at the intersection, you ask a little bit newer questions. So it's a lot of low-hanging fruit, which I think is very accessible to students. So in my group, we have often, like I said, high school interns even, but mostly, maybe undergrad researchers and PhD students. I think it's a very accessible field, which lives off more of creativity rather than kind of mathematical complexity.
Well, on this optimistic and somehow positive note, I guess it's a good time to conclude our conversation, if you agree. And I sincerely thank you for your time and help. You got me super excited. I'm closing Zoom with a very good mood today.
Thank you. I'm very glad. I'm excited too, and I'm glad to share this. But I really think there's so many interesting developments still ahead of us. So it's a fun time to do this research and hopefully encourage at least some students to explore it. Yeah, thank you so much for your interest.
No, thank you, and I'm sure many of our viewers will have a lot of questions to ask. So let's see when the interview will be published on YouTube.
Fantastic. I'm happy, of course, to reach out or even revise. Many of these questions, I would say, are actually very deep, because the simple questions are the ones that really matter. And then finding the good answers is, in some sense, the equivalent to doing the research in this field.
I fully agree on that. I fully agree on that. And that
Thank you,
being
David.
said,
Sorry, yeah, go ahead.
no, that being said, I hope to see you soon. And thank you again for your time and help and cooperation with this.
Thanks for your interest. Yeah, and I'll see you soon. I see you in July, the latest.
Yes, I didn't want to spoil that, but maybe in July we can we can
Right.
do
Yeah,
something in person if you agree.
of course, that will be great. Yeah, but yes, exactly. And then if anything else is needed, let me know. That was a
Thank
lot of
you.
fun.
Thank you very much.